Welcome everybody to the language webinar series. Okay, this is a series of monthly webinars that we have going on. Today we have with us Goran Glavaš.
Thanks a lot for the invitation. I'm happy to give you kind of an overview of some of the recent things we've been doing in my group. So I have a professorship or a chair for natural language processing at the University of Würzburg in Germany. Those of you who might have not have heard of Würzburg before, it's a town of 100 and something thousand people, halfway between Frankfurt and Nuremberg. Yeah, there's a kind of like a critical mass of AI people building up here. There is some funding from the state of Bavaria, and my position was one of those. I've been here now somewhat over 3 years, and I'll be talking about multilinguality, which is kind of like a dominant topic of research in my lab. But as you'll see throughout the talk, we look at multilingual abilities of not just the classic standard language models, text-based language models, but also some other types of language models. Okay, then let me dig into it. So we all know that LLMs are at the core of everything meaningful in AI these days, and the commercial LLMs can reason, solve complex problems. They can behave as agents. They can use tools. They can self-reflect and self-improve through interaction. And they've gotten so good that they can actually solve gold medals in Math Olympiad. But when you move beyond English, a lot of these reasoning abilities, or a lot of these very advanced abilities of LLMs, or when you move at least beyond the top 50 or top 100 languages with most text, you start see that they don't just lose these advanced abilities, they actually fail on much simpler tasks. So if you ask, just as an example, a ChatGPT to do, or that was a GPT-4 concretely as a model, to do named entity recognition on a newspaper text, which is a mainstream domain, kind of in Romani, which is a language with 10 to 12 million people, million native speakers across Europe, Roma people, then basically what it gets you out is complete nonsense and not a list of named entities that occurred in that text. So we kind of know that the LLMs are exclusive if you look at the set of languages that they kind of support. If you think of these abilities that I mentioned first, complex reasoning, long context reasoning, multi-step reasoning, chain of thought, planning, and so on, you're going to see strong support for those in really a handful of languages. Then for more, let's say, natural language understanding tasks or standard NLP tasks like summarization or translation or some kind of inference, you're going to see some more support, maybe for 100 or so languages, but for the vast majority of the world languages, not even the state-of-the-art LLMs can do anything. And it's no secret why this is the case, right? So we know that their performance for any particular language is bound with the amount of text data that they've seen in that language in pre-training. So the bitter lesson of AI is something it's a blog post from, I think, 2019 by Rich Sutton, who is a famous researcher, mostly in reinforcement learning. And that, I think, is very strongly connected with multilinguality. And what he says is that the biggest lesson from 70 years of AI research is that, you know, we've seen improvements with fairly general methods once we were able to let them leverage more compute. And you know, conceptual improvements or conceptual innovations were more like small things in the development process, but they never brought huge gains. So it was compute and data scaling that improved things, that brought, you know, discrete jumps in the abilities of AI models over time. Here's an image. I like to do my talks somewhat interactively, so if someone is willing to answer the questions I might ask here and there, then I'll be happy. So here's a depiction of a neural language model. Does anyone know which year it's from? Would anyone like to guess the year, or maybe which exact model it is? It's a neural language model.
We have one guess in the chat, Bingio 2003.
Yep, that's the one. Very good. If you look at the structure of that language model, there's an embedding layer with inputs. So you have trainable vectors for the words. Then you have something of a rudimentary encoder. So it was just a concatenation of the word embeddings and then a nonlinear operation on that. And then you have what we would call today an LM head, language modeling head. Basically, again, a layer that produces the distribution over the vocabulary given your representation of the input context. So one could argue that the LLMs that we use today conceptually aren't really any different from this. Yes, the encoder body's got more complex. Yes, it's a transformer architecture. Yes, there are positional embeddings. Yes, there are many things added. But if you look if you zoom out a little bit, the high level concept is exactly the same. So if scale is what brought the progress, then the obvious question is scale the only answer? And if it is, then we can just say that the vast majority of human languages are just sentenced not to have a language technology support ever, full stop, right? LLMs are expensive to train. There are now more and more training steps. Each of them becomes increasingly more data hungry and increasingly more expensive. So there's the autoregressive language modeling pre-training, there's the instruction tuning, there's the alignment or preference learning. And while you execute all these steps, if you want to have a competitive LM or an LLM, you need quite some money. Does anyone have a guess what is the cost today of pre-training a somewhat competitive LLM? I'm not saying a Gemini or GPT-5, but something that would be, let's say, competitively performing open LLM of a few billion parameters. Doesn't have to be a 70 or 100 billion. We're talking about 1 to 10 billion parameters. A guess, a ballpark estimate from anyone?
$1 million for 7B we have?
Yeah, a few million maybe. Yeah, I don't know the exact answer. I don't have a concrete reference, but when I looked at some estimates, it was a couple of million that you needed at least. We had some colleagues here who have trained from scratch a 7B German LLM, German only, on, if I'm not mistaken, like a few 100 billion tokens. And that, when we roughly converted that into how much the compute cost, of course, the state funded and everything, but that did convert into something like close to €1 million. So how do you level the playing field? Obviously, the big tech or the industry has the resources to scale the compute more or less arbitrarily, but they cannot scale the data arbitrarily, at least not for the long tail languages, right? Because that data simply doesn't exist in abundance. So what my talk is going to be about is kind of like a bunch of tricks and things that we've done to improve things for less resource languages that are not about the scale only. And I'm going to focus on 3 types of language models. So first, the standard ones, the text-based multilingual LLMs and cross-lingual transfer. So when you learn something in a particular language and you hope to use that ability on instances from other languages. But in the second and third part, I'll focus on other types of language models, multilingual vision language models. So when there's visual input in addition to that. And then at the end, shortly, something on code LLMs, so language models for coding. So one of the primary motivations why we want to have multilingual language models and not a monolingual language model for each language is that, when you have data for a particular task and when you fine tune a model for a particular task, no matter how big, you still get the optimal performance for that task. So what we'd like to have, knowing that we won't have task-specific data in all the languages that we would like to support, we would like to have some underlying multilingual model that once we use task-specific data in a high-resource language like English, hopefully this underlying multilinguality allows us to execute that same task in other languages. Here, for example, sentiment on the slide. In theory, if you train your language model multilingually, meaning you concatenate the corpora of many languages and then you train the model is supposed to, quotation marks, understand many 100+ languages. In practice, and this is something that was established a long time ago, one of our popular papers from now an eternity ago, 5 years ago, was showing that as soon as you move to target languages, even though some of these are high resource languages, they've been seen by multilingual BERT or XLMR in pre-training a lot, you get massive performance drops. What we then also showed is that there is a cheap fix to that. So if you can collect even just a little bit of task-specific data in that language, that's actually very efficient. You can get high performance gains. You can increase your performance quite a lot, at least for back then the lower level tasks that we were examining, with as little as 10 or 50 instances in the target language. And this, if you think of it, is much cheaper. So even my language is, my language model is multilingual. I can transfer to some extent, but I see drops. And then I need to improve it for a language that is underrepresented in the representation space of your multilingual BERT or XLMR. One option is I go into continued pre-training. I get more data in the language that is underrepresented and where my model performs badly, and I try to train more for it. That's fairly expensive. Or for a task that I'm particularly interested in, I get a few labeled instances in that target language. And we show that the second thing is surprisingly effective and much cheaper than going into any kind of continued pre-training for your underlying language model. Now, this is old, but the idea is still highly relevant, and I'll make some comments on that later on. So in the follow-up work, we actually propose a strategy where you don't do this sequentially. So you don't do fine-tuning first on your high resource language and then on a few instances from your target language, but rather you interleave your few target language instances in the batches together with the high resource language instances. So you have plenty of English data for sentiment, and you have a little bit of Croatian data for sentiment, and you tangle in these few instances in low resource language or lower resource language, and then you get better results than if you do it sequentially. There are tricks or preconditions for that to be successful, and that's balancing the contributions to the loss at the batch level. Even though you have fewer instances in the target language, you keep repeating them more frequently to make batches balance between the two languages. And you might think that that will lead to overfitting to these few instances that you have in the target language, but surprisingly it doesn't. And it doesn't because these few target language instances here, in every batch where you keep repeating them because you have only a few of them, they are contextualized, or not contextualized, but put together with a different set of instances in the source language. And when you aggregate the loss, it kind of the different source language instances provide a form of regularization, and you end up with better results. Okay, but some of you might be wondering, why am I talking about BERT, XLMR encoders? Isn't that age of NLP over? Maybe you're aware of actually increased efforts where there is a trend in the community to go back towards the encoder models for various reasons. There are tasks at which they are better than decoders. They're much better embedders for all kinds of retrieval tasks. They can be trained to be useful for NLU tasks, even if they're much smaller than the billion parameter sized decoder models, and so on. So there are efforts like Modern Multilingual BERT that came out only a few months ago, where they actually train for a huge number of languages, 1,800 languages. And then the question is, do these problems that I mentioned still persist? The trick that they introduce here is that they say, okay, we have a particular curriculum of training where we only train initially on a smaller set of high resource languages. Then as we go sequentially, we keep balancing out the distribution over the corpora and introducing the lower and lower resource languages, so that if they're seen later in training, their small contributions in terms of corpora can still matter in the final representation space of the model. I'm not fully convinced that this is really super good for the low research languages and that the curriculum is everything we needed. And also the evaluation is somewhat questionable, I would say. Most of the results that they report are on fairly old NLU data sets, and the 3 trillion token corpus on which they pre-trained the model might very well contain those exact tasks and data sets in there. Also, there are few in the evaluation itself. In the training, yes, there are 1,800 languages, but in the evaluation itself, there are few that are truly low resource. So moving back to the LLMs, which are still the main hype, one could argue that large language models are actually even more English-centric than the earlier encoder-based LLMs. And that's because when you want to get these emerging properties at scale, you cannot afford to downsample your English so that the proportion of your smaller languages grow, right? You need all of your English data or all of your high resource language data. So what we were thinking of is, can we, as many others did, how can we best or optimally and with the cheapest effort remedy them post hoc? And if you think of it, LLMs are English-centric, but you have another category of models, and these are machine translation models, and they're encoders in particular, if they are sequence-to-sequence models, that are actually very good at aligning meaning across languages. So can we somehow patch together a language modeling, a machine translation encoder to an English-centric LLM and get a hybrid, a Frankenstein that is somehow able to do NLU better for all the other languages that are supported by the MT encoder? So here's a rough idea. This is your LLM. This is your LLM, its embeddings and the body, transformer layers, pooling, and something comes out as a representation for the entire input sequence. At the same time, you have a machine translation model, and we take its encoder. So something like NLLB, this is no language left behind OpenMT model. You take its encoder, not the decoder, just the encoder, but the representation spaces of individual languages here in the encoder should be better than in the LLM, right? We know that they are. So can we somehow, if we can somehow put this and make the LLM body, the transformer of the Anglo-centric LLM, understand this input here instead of the LLM's own embeddings, which of course there will be a representational mismatch here, but can we do something to train the body of the LLM to actually get used to the inputs coming from the MT encoder instead of being its own embeddings? And there's a fairly simple strategy that works, and that's what we call self-distillation. So you just feed the same input through the LLM as a whole, right? LLM as it is with its own embeddings. Then you feed it through the Frankenstein, so NLLB merged to the LLM's body. And then you let the LLM be updated via the LoRa fine-tuning, so parameter-efficient fine-tuning. And what you want is your representations coming out at individual layers. You can impose this at each layer of the transformer. You want to say, I want it to be the same. I want the LLM to be able to produce the same representations when it gets the input from the NLLB encoder as it produces when it gets its own embeddings as input. And just the MSC loss actually worked quite well here. You can do this both as a kind of a pre-training alignment step and also in task-specific fine-tuning. And we kind of see that we get it to align with the input with the NLB encoder well enough so that then you can feed the inputs in all other languages in, because they're well aligned with the English representation space in the NLB encoder, and the LLM can then do better for those languages. The best part is actually that the self-distillation process can be executed completely you don't need label data and you don't need data in other languages. So it can just be arbitrary sentences in English. So you might be thinking, some of you, if someone is working on machine translation or on cross-lingual transfer, well, why would you do this Frankenstein between you take only the encoder of an MT model and you try to merge it to the LLM so that the LLM can understand its outputs. Why don't you just translate the text? Let the LLM generate everything. Let the LLM make predictions, generate everything in English, and then translate. Translate test. You get the test time instance in the other language. You let it be translated by your MT model to English, and you make a prediction for the English input. That's what is called in translation-based cross-lingual transfer. This is a common baseline. This is called translate test. And this, of course, was the main baseline in our experiments as well. So instead of, we take the same MT model, but now with its decoder part as well, so the full MT model. The same MT model from which we separated the encoder for our hybrid. And we use that as the baseline. And not going to dig deeper, but these are various language understanding benchmarks for various groups of low resource languages. These are, for example, Turkic languages, Bele is 100-something diverse languages, and so on. And we see improvements. So soft integration of an MT encoder to an LLM is better than just doing hard translation with a full MT model and then feeding the English translation into the LLM. This links to another line of work that we've been pursuing, and that's, is machine translation all we need for cross-lingual transfer? Why, if the MT is good enough, if you have enough parallel data for a pair of languages, why would you struggle to do any kind of representational alignment within the language models, right? You just do everything monolingual in English, and as you need it, you do translations back and forth to your other languages. We actually show in some of our work, and this is just to mention that there is this body of work that they are highly effective, these translation-based XLT approaches, and they're highly effective for low resource languages. Low resource in the sense that there is an MT model that is of a certain quality, but the language itself has not that much pre-training data for multilingual language models, right? So that the pure transfer with the language model is not as good as the MT-based cross-lingual transfer. And we even show that if you have languages that are not supported by the MT model, so NLLB supports 200 languages. I think MadLad is maybe the most multilingual at the moment with 400 something languages, but 400 is still much less than 7,000. So there are many languages not supported by the MT model. What we tried is pretend that, for a language that's not supported, we look at typological properties. We find the most similar language in terms of language family and typological properties, and we say, okay, the most similar supported language. And even that works better than, just transfer with the language model. Okay, so much for the first part of my talk on multilinguality in standard language models and cross-lingual transfer. The second bit moves towards vision language models and also primarily multilinguality there. This is what we're interested in. Maybe just as an introduction for those of you who don't work with vision data, what are vision language models and what's the landscape from a very high level perspective? You get an input which is an image or visual input and or text. So it could be just an image, it could be just text, it could be both. Some type of vision language foundation model is then used to either produce the embedding, so to encode your image and your text, and then you do either retrieval or some kind of clustering. And these are the embedding models, the clip-like kind of models. Maybe probably you've heard of clip. And then there are the other category of models where you don't want to just embed, but you want to actually generate answers, generate captions for images, or generate answers to questions about images, visual question answering. And here the predominant paradigm is that you try to align a visual encoder to your existing LLM, because your existing LLM is very good at reasoning and also at generating language, right? So that's the common course of action. And then there's the third category where you want to generate images or edit images based on existing images and textual description prompt of a change to an image, but that's not something that we do. That's more in the vision realm, so image generation. Okay, so our research focus is on the encoder models as well as the vision LLMs. They both still have applications, meaningful applications. And what we focus on is multilinguality, also aspects of trustworthiness, reducing hallucinations, and improving, especially in the multilingual realm, the evaluation protocols and expanding the set of languages where you can evaluate something for. So the first line of work that we did was focusing on the encoder models, CLIP. Maybe just briefly, for those of you who might not be familiar with the CLIP, you have two transformers, one that encodes text and the other one that encodes images. Strictly speaking, this doesn't have to be an encoder transform architecture, but most commonly it is. And then you have a lot of image caption pairs or image text pairs from the web, hundreds of millions to billions. And you're training these two encoders to produce matching representations. And you're training them contrastively so that when you compare the embedding of a text and an image that do fit together, so image 1 and text 1, that score should be higher than everything here where the image was compared to the non-matching text, and everything here where the text was compared with the non-matching images. So using that contrastive training on billions of image caption pairs, you get encoders of the text and image that produce semantically somewhat aligned representations, so that you can search for captions given an image, or for an image given a text, or image given an image and text given text, but that's not a common application. So searching, filtering, classifying, clustering, so things that you can do efficiently if you have a semantically rich embedding of an image and text. Now, but when we started looking into these models and how multilingual they really are, there were many readily available CLIP models. Many of them were also massively multilingual, typically derived by initializing this text encoder with multilingual LM, XLMR or MBERT or something like that. So what we wanted to know is which one is the best, what is the best, and whether we can improve it for languages where they don't perform so well. So we tried to look for very multilingual evaluation benchmarks, and we couldn't find really any that were very multilingual. You had image text retrieval benchmarks, which at the time were encompassing something like 30 to 40 languages at best. And then you had zero-shot image classification. That means there's an image, you give a label as text, and you compare whether they match, and if they match sufficiently, you declare that you have a dog in the image because the embedding of the text dog and the embedding of this image had high similarity. The problem is that most evaluation benchmarks were mostly in English, and we set to build kind of like a very massively multilingual benchmark for evaluating CLIP-like models. But how do you obtain a massively multilingual data set for something like zero-shot image classification? Here, machine translation is not really an option, because if you have something like, a walking stick, which is a type of a bug on this image, and you translate that concept out of context, of course, you're going to have in the target language a literal translation of the main sense of this concept, and that's not the correct translation in the target language. So there's a lot of noise when you translate, if you use MT to translate concepts out of context. So what we thought might make sense is to use ImageNet and BabelNet together, figuring out that they're both based on WordNet concepts. So ImageNet is just WordNet synsets in expanded with images. And BabelNet is a massively multilingual version of ImageNet in a sense. So we could use the sense IDs to match images from ImageNet with multilingual synsets in BabelNet, which were reasonably clean. And we could actually that way derive then a massively multilingual and reasonably reliable benchmark for zero-shot image classification. And then we simply benchmarked a bunch of multilingual CLIP models, and for all of them, when we group the languages basically based on resourceness, from English to very low, a few buckets of language resourceness, we got the expected results, performance being much higher for English and high resource languages than for the low resource languages. So what we wanted to do is, again, not having resources to go into any kind of training a CLIP model from scratch and balancing out the training data across languages. We were most interested in how can we cheaply post hoc fix the representations or improve the performance for a particular language that you might care about. So we did this independently for 16 very low resource languages, and the strategy was fairly simple and, most importantly, computationally cheap. So if I have a pair of data, if I have a translation pair, which you can get via MT, in your high resource language and your low resource language, then you can basically enforce your multilingual text encoder. This is the same block, just depicted twice. The representations that it produces for a low resource language like HOSA and the one that it produces for English should match. That's one source for your objective for better alignment, but you have an image and you know that that image should match both variants of the captions, right? So you can also enforce representation alignment losses. Now there's a variety of them that we played with between the image representation and both of the representations, but primarily the one that comes for the caption in the low resource language. So by doing that, we actually show that with very little training, you can dramatically improve performance for low resource languages. So here's just a sample of low resource languages, and these below the lines are basically these are the baselines without additional training that we did, and this is what you get with different objectives that we introduce, and we get massive gains for the lowest resource languages with very limited training. Okay, embedding models like CLIP are useful for tasks like retrieval or classification, but there are very many vision language tasks that you simply can't address with an embedding model. And there you have, for example, visual reasoning, visual question answering, visual natural language inference. So you have an image and then a hypothesis that a statement about that image, and you need to say whether the statement follows from the image or it's contradicted by the image. You need to answer questions about images, or you might need to reason about combinations of images even, right? There are 7 people together in these 2 images, true or false, right? So for these kind of models, the main tool in the shed that you would take these days are the so-called vision LLMs. So you align a pre-trained image encoder to an LLM. Why? Because you also want to have instruction tuning in a sense, and LLMs have been instruction tuned. Many of them, they know how to follow instructions, and you want to be able to generalize to new types of vision language tasks as well. So this is typically done in 2 steps. In the first step, you align an image encoder to an LLM. This is called the pre-training, and to do that, you typically do just image captioning. Your image encoder is frozen. Your language modeling, your LLM is frozen. And the only thing you're training is something here called an alignment module. In the earlier days, as depicted here, these alignment modules were some kind of transformers themselves that were producing some kind of transform representations of visual tokens. These days, they have been simplified architecturally. It's been shown that you can just go with some kind of a feed-forward network, and that suffices. After you do some kind of pre-alignment, so that whatever comes from an image is kind of understandable to the LLM, then you step into the instruction tuning. You take all the different vision language tasks with instructions and the data sets that exist out there, and you go with this instruction tuning mix into the training. And that all sounds good. At the time we started doing this line of work, the assumption was that we just thought, let's pick something multilingual and evaluate it more thoroughly or more widely multilingually, and then we couldn't find anything other than PaLiX. At the time, this was 23 roughly. So the only multilingual ones out there were not open. So we set for ourselves a goal to obtain a competitive multilingual vision LLM, but of course, given our limited academic resources, so again, in a sample and compute efficient manner. So to get some kind of efficiency, we started from this alignment component. We just initialized it from a model, from an already aligned English-only model, right? This might be detrimental for low resource languages, but still the alignment between a visual information and an LLM is something that will somewhat, because of the language agnostic nature of images, probably be beneficial if you go into then multilingual training in the second step. So that was our assumption. And then in step 2, we applied this multilingual instruction tuning. The problem, however, if I go back, this is what I circled here, that these instruction tuning data sets were not really multilingual. This was predominantly English data. So how do you get instruction tuning data multilingual? And then, of course, if you don't have a better solution, take off the shelf an MT model and translate all the instances, all the captions, questions, and so on, all the text data in these tasks with an MT model. And then that's what we did. We trained in the second step on the synthetic MT obtained data in a bunch of languages, and not going to go into the detail of the results. There's many of them, but at the time we kind of like, if you additionally fine-tune then in the evaluation setup for a particular task, we were competitive with the state of the art at the time. Most critically, or an important point here, is that we achieved this with very limited training. So 4 consumer level cards and 4 days of training on them. So this was the first multilingual language image alignment model, which was called MBLIP, or the previous models, English-only models, were called BLIP. So MBLIP was a multilingual extension that we produced. But then we wanted to dig deeper. And this is the paper from this year's ACL, where we actually try to decouple things a little bit. So what drives the multilingual ability of these large vision language models? You have the pre-training data, and we group them into a couple of languages, into a couple of buckets based on language resourceness. Then we wanted to see, does it matter which languages you have, to which extent in this pre-training and instruction tuning? What's the language distribution between English and non-English languages? And then for the non-English portion, we always had an equal division between the number of languages included. Until which extent can we increase the number of languages included in this instruction tuning without observing a drop in performance in each of them? So the curse of multilinguality. And finally, the last bit that we were interested in, this is kind of orthogonal to the other research questions, but can we do better for images that actually have a lot of text content in them? And there we created some synthetic data to train for this. So we were searching for the optimal recipe. How many languages to actually train with, and how many can you keep adding without reducing the performance for each of them? What percentage of your data should be in English and which in non-English? Non-English portions were always equally split between the languages. Then the similar question for the pre-training step, where we just use captioning as in the instruction tuning. And finally, this focus on the text and image performance, so text-heavy images and answering questions for them. And especially if the text in the images was not in a Latin script. So we did a lot of experiments to inform each of these research questions. And then when we find the optimal recipe, the optimal ratios, we went into a larger scale training with that optimal recipe. We trained 2 models with 2 different LLM backbones, models that at the time when we started training this, were considered most multilingual, the LLMs, IA-Expanse and Qwen 2.5. And then we evaluated across 100 languages on 14 vision language tasks. We grouped them into buckets by resourceness again. And we show that across most buckets, we had the state-of-the-art performance. Again, things have developed since this summer, so this is probably no longer the case, but it also goes to show that it is possible when you're in the multilingual realm, even with images and vision, with limited academic resources, to push somewhat the results. Okay, if I'm not mistaken, I have something like 5 minutes left, or 5 to 10 minutes left. So a bit of again, a context switch, but the main topic remains multilinguality. It's about multilingual code language models. Code language models, I would assume that most of you do use them on a daily basis. I certainly do. Most of my PhD students do. You just use Copilot in your VS Code or whatever you prefer. They boost productivity for software developers. You can interact, they follow instructions. You have general purpose LLMs, which are very good at code generation because code is carefully sampled or even upsampled in their training steps from pre-training to preference learning. Then there are also specialized code language models and so on. So it's a very useful family of models. However, if we look at the distribution of different programming languages that exist in the world and how much data there is across them, we will notice actually that distribution is far more skewed than the distribution of natural languages if we're talking about training multilingual text-based LLMs. So for code, it's actually much worse. And similarly as for natural languages, for tail programming languages, you see that all of these code LLMs actually drop in performance dramatically. One example, DeepSeek Coder, if you wanted to generate Bash scripts instead of Python code, you get performance drops of 30%. So what we wanted to do is, of course, improve the performance for the long-tail programming languages. And one idea that we followed here that was fairly successful is to use some kind of an interlingua between the programming languages to ground them all. And if you can ground them all to the same representation, then the information flow, the positive, then you're essentially facilitating the cross-lingual transfer, positive cross-lingual transfer between the programming languages. The advantage, of course, when you're working with code is that unlike with natural languages, where people have for decades been researching what might be, this formal interlingua that we can map all natural languages into, and then all we need to do is work on this interlingua. With code, you naturally have interlingua, and these are these intermediate representations that your code in your source language is compiled into. So there is a lot of tools out there and a lot of options for this intermediate representations to get out of the compilers. What we worked with is one particular called LLVM-IR, and the intermediate representation that we get. So this is the intermediate representation from this small snippet of original code. What we created was basically pairs of original source code and the corresponding LLVM-IR. Of course, then you can compile source codes of many different programming languages into the same intermediate language. Once you have those pairs, you can then hope that having this same intermediate representation paired with the different types of programming languages, source programming languages, you need some kind of a training objective to align, to ground the source programming languages in this representation, and hopefully things then get more aligned between the programming languages. So what we did as in terms of a grounding objective was something as rudimentary as it goes. So when we had these pairs of source and intermediate code, we just concatenated them, had some kind of special token in between them, and we did causal language modeling. Now we had two types of concatenations where we first put source code and then we put the intermediate representation code. or the other way around, so that both ways are seen when you do causal language modeling, and then you continue. It was a continued training starting from some existing code LLM. A lot of the evaluations that were highly multilingual, these are all fairly standard code LM evaluation benchmarks and code LM evaluation metrics, without going into details of what they are. Across, starting from initial models of various sizes and doing this kind of intermediate representation training, we got across the board improvements, from higher to lower improvements, but generally across the board significant improvements on a variety of multilingual code generation and code understanding benchmarks. And in particular, the gains were, of course, the largest on the programming languages that were least represented in the pre-training of this code LLMs. Okay, so I started with a beta lesson, and I'll try to conclude in a more optimistic tone. I think some of the work that we've done and some of the other work in the field shows that the lesson is maybe not so beta ultimately. So scale is the only answer, or it's hard to beat the scale if you're speaking English and coding in Python. So if there isn't much conceptual innovation, but you can scale things up in terms of data and compute, yes, you will get quite some gains. But if you cannot, what happens if you cannot scale? And if you step into the multilingual realm and move beyond top 100 languages, then you start getting into a space where conceptual innovation might actually be interesting. Scaling up data is harder, also for industry, not just for academia, than scaling up computation. And multilinguality is a setup where data is the primary bottleneck, which means this opens more possibilities for conceptual innovation and not just to progress by scaling things up. And this leads me to what we're currently exploring. I think the key strategies for really making a substantial differences in the multilingual realm and for low resource languages is to enable a much more effective cross-lingual transfer than what we have in current models. How to do that is, of course, the key question. Unlike for code, where we have rather cheaply, we can get this interlingua, these representations that all programming languages can be mapped to. This doesn't exist for natural languages, right? Searching for an interlingua could be the summary of 50 years of efforts in multilingual natural language processing. We have some ideas. We're currently working on some ideas. In a nutshell, we're thinking in the direction of multilingual discrete text diffusion models and how to use parallel data optimally there, how to use concept-based alignments from BabelNet, to have auxiliary objectives that can better steer the representation alignment, and then hopefully get significantly more effective cross-lingual transfer. The critical thing for when you don't have the data, this is the fundamentals of machine learning, is that if you can find good inductive biases for languages where you have little data, then your training on that little data will be more effective. You get more sample efficient training. You get more out of your limited size training data. What are the good inductive biases? That's also a very open question, an open area of research. I tend to believe that we do have a lot of resources for thousands of low resource languages where you don't have much text, but you have dictionaries, you have typological descriptors for these languages. And my gut feeling is that these resources are still not leveraged to their full potential. And they do represent a type of inductive bias that could make the language modeling training more sample efficient. With that, in somewhat more optimistic tone than what I opened with, I'd conclude my talk and happy to go into a discussion.
Okay, thanks a lot, Goran. Super interesting talk. So if anybody has any questions, feel free to raise your hand or write directly in the chat. and I can either read it out or I can let you ask your question. Okay. So let's see, anyone? No questions right now. Yeah, I'll start off with one question that I had. So you ended your talk talking about this, let's say, need to find an interesting inductive bias to kind of help with this transfer across languages, multilingualism. One thing we used to use, at least back in the day, was when we didn't have a whole lot of data, we had expert knowledge. We could either write rules, we could have some linguistic representations, some small amount of annotated data across languages. But we seem to have kind of moved on from that right now. Do you think there's any room for that kind of expert knowledge still to work as an inductive bias?
Oh yeah, depends. I mean, what you named are two different things. Having some small amount of label data, maybe it's something very syntactic, or some dependency trees, or some sequences of parse speech data, and so on. That's somewhat different from having kind of like a typological descriptor of a language, right? Like these URL vectors or world atlas of language structures, where linguists have coded, different properties, linguistic properties, word order, this and that for thousands of languages. The label data, even if it's like very linguistic, it simply doesn't exist for thousands of languages. You're not going to find any syntactic structures or anything like that. On the other hand, the typological properties have been used in a variety of works, some of our own that I haven't presented here, to basically improve the initialization. So if I have typological descriptors for many languages, I can integrate them in the training for high resource languages that I have in my multilingual LM training. And then when I need to train or predict something for a language where I have very little data, but I still have a typological descriptor, I would hope that my model has learned to generalize over these typological descriptors, right? So it will give me some kind of meaningful initial parameters for an unseen language. If I'm being honest, the gains from that did exist, but they were marginal.
Yeah.
So it's not, yeah. One other thing comes to mind. Recently, people are looking into, so LLMs are great reasoners, right? So most languages, they have, some linguist went, even if it's something that's only spoken by an indigenous tribe somewhere on Papua New Guinea, there has been a linguist, a field linguist, who went in there, recorded, and wrote a book about it, right? That documents some structures and so on. And with LLMs being great reasoners and having longer and longer contexts, there is now work popping up showing that, hey, here's a book on this language you've never heard about, but here's a book in English that documents that language with some examples in there. Can you do stuff now in that language, right? You almighty LLM. But that's also, I would say, broad limited gain so far.
Okay. Do you think is that just because of the let's say quality of the annotation, the level of annotation, or is it just a problem of not having, or is it a different kind of problem? Like, I mean, if you had perfect, let's say, typologies with all of the important qualitative information about each language, would that help more, or is it just a problem of having too much information, maybe that's not compatible?
Yeah, that's a very good question. I think it really depends, help for what. And I don't think, I'm deeply convinced that you can't have meaningful language generation for languages without text. I mean, languages are very, very complex distributions. And we see that they are very, very complex distributions because for languages where we have enough text, we need, petabytes of data and models with billions of parameters to actually to have models that can actually produce language at a human quality. So they're very, very complex distributions, and if you can't see a lot of examples of something, we're estimating that distribution from the data, then you can't produce meaningful sequences of something you've never seen, right? So I think for language generation scenarios, I am deeply convinced that there is no meaningful language generation for languages where you don't have text data, full stop. But for language understanding, when you need to predict something from the text, and there are more difficult and less difficult tasks, if we're talking about something like topical classification, then resources like dictionaries, which do exist for thousands of languages, typological properties, this and that, could be strong enough of a signal for maybe simpler language understanding tasks. And there you could see gains for a lot of languages.
Okay. Really nice answer. So we have a couple of questions in the chat, and maybe we have time for 1 or 2 questions if you have time.
Sure. Yeah.
Okay. So Pavel was asking, does using the same group languages, I guess, in one batch help? I imagine this means groups as in linguistic families.
As in genealogically or typologically grouped languages. Yeah. So in short answer is yes. So if you transfer, there are many low resource languages that you can do reasonably well for, because they have high resource close relatives, right? So Faroese is an example of a language that you can do. That's a very low resource language, but you can do very well because it's very close to Icelandic and all the other Scandinavian languages, which are in turn Germanic languages. So you get a lot of useful propagation also from English and German and Dutch and so on. So that's a different problem from dealing with a low resource language from some, let's say, Papua New Guinea, Trans-New Guinea family, where in the whole family of 1,000 languages, there isn't any that's high resource. Like you don't have a high resource relative. We've done some work for Turkic languages. Many would consider, and it is definitely a high resource language. Turkish is a high resource language, but pretty much everything else in that language family is low resource. Mm-hmm. And if you include Turkish, or if you try to transfer from Turkish, or you include mixed Turkish with English in all kinds of training scenarios, you do get better transfer to other Turkic languages. So yeah, short answer is yes, as long as you have a relative in the language family that is high resource.
Okay, thanks. And then maybe one last one. Victor asks, could it be that a specific field, could a specific field in a language be considered low resource? For example, I don't know, the healthcare field or something like this, where even though you have an LLM that works for that language, it doesn't work necessarily for that specific kind of domain.
Yeah. So those are low resource domains, right? And you can have all combinations, low resource language and a low resource domain, high resource language and a low resource domain. Anything that's out of the distribution compared to the pre-training data you're going to see a performance drop. So for the low resource domains, or the domains that are different from pre-training data, specialized domains, some of the problems are the same. Essentially, your vocabulary shifts a lot, right? You start getting tokens that have had really low frequency in pre-training. Suddenly they are, medical terms that are highly frequent in your medical domain. So some nature of the problem is the same, but it's still the same language, right? So it's easier to adapt to a domain in a high resource language to a low resource domain than to adapt from a high resource language to a low resource language that has a completely different vocabulary, possibly a completely different script, and so on. So there are similarities, but it's a simpler problem. The domain adaptation, in my opinion, is within a high resource language is a simpler problem than adaptation to a low resource, unseen or barely seen language.
Okay. Maybe one last short question, which Julian asks is, which approach do you think is the best to create, either to create VLMs for low resource languages from scratch, or to adapt ones that already exist?
Oh, to adapt. I mean, VLMs, again, as LMs, I mean, you do get visual understanding from image encoding models, which are language agnostic. They have nothing to do. But this alignment step also requires quite a lot of data, which you're not going to find in a low resource language. Now, if your lower resource language has a reliable MT model, and you can basically translate an arbitrary amount of English instruction tuning data, then you might be well off with a monolingual model for a low resource language. But then some people would argue, if you have a reliable MT model for a language, then that's not a low resource language, right? So So kind of chicken and the egg. What we've seen in the Centurio work, that was kind of the point, to see that if we add more and more languages that we can get data, reasonably good data with MT, if we add more and more into the mix, what happens? And we didn't see any drop after any point of languages added, which means that there is no, at least based on our experiments, there is no downside to training multilingually, including additionally the data of that language compared to training for just that language, right?
Okay. All right. Well, thanks a lot. Thanks for the great talk and for the discussion. I mean, it was really, really nice to have you here, Aziz. So,
Thanks for having me. I'll stop sharing
absolutely.
now. Just
Again,
yeah.
Sorry for the beginning, the shaky beginning. Just
yeah, no worries, no problem at all. Thanks for inviting me. Thanks for having me, and thanks for the interesting questions as well.